Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
It's so easy when you step outside on a clear night and look up. It is incredibly easy to fall into this psychological trap of thinking about space as just this quiet, echoing void.
Right, yeah. Like it's just endless emptiness.
Exactly. Just a massive expanse with a few major planets scattered around in the dark. But I mean, if you actually zoom in on our immediate cosmic neighborhood, the physical reality is, oh no, it's entirely different.
It's crowded.
It is bustling. Right now, as we speak, there are tens of thousands of near-Earth objects, NEOs just tumbling through the dark right in our backyard.
Yeah, and we're talking about miniature worlds here. Some are the size of a city block. Others are the size of a mountain.
Right, and these aren't just, scientific curiosities for us to map and then forget about. For you listening, think of these as the most easily accessible resource caches in the entire solar system.
Absolutely. Heavy metals, rare earth elements.
Volatile compounds, water, ice for in situ resource utilization. They're practically right next door, astronomically speaking. But the catch, and it's a huge catch, to actually reaching them is massive.
It really is.
Because figuring out the astrodynamics, like how to mathematically plot a path, drive up to one of these rocks and actually park next to it, is a notoriously mind-bendingly difficult problem.
Okay, let's unpack this.
Yeah, it remains one of the supreme challenges in aerospace engineering. Because the assumption by a lot of people is often that, well, since space is a vacuum devoid of atmospheric friction, you simply aim your thrust vector at the target, rendezvous coordinates and just let momentum do the rest.
Just point and shoot, right? Like a bullet.
Exactly. But the reality of astrodynamics is governed by this chaotic web of n-body gravitational interactions. Every planetary mass, every moon, the sun itself, they are all constantly warping the space-time around them.
They're all pulling at once. Right. They're exerting these dynamic gravitational pulls. So calculating a viable, fuel-efficient path through that constantly shifting gravitational topography has historically been one of the tightest bottlenecks in mission planning.
It sounds like a nightmare.
You are essentially trying to thread a needle, right? But the needle is moving at tens of thousands of miles an hour, and the thread is constantly being pulled by invisible magnets from every direction.
Man, that is a great visual, which makes the recent work coming out of Khalifa University so incredibly compelling. Alessandro Biolci and his co-authors, they put this out on our sleeve. They've effectively rewritten the fundamental mathematical roadmaps we use to navigate deep space.
It's a massive deal.
And just to be clear, this isn't some minor optimization of existing software. They haven't just, tweaked a fuel mixture or shaved a few kilograms off a chassis.
No, not at all.
They are proposing a wholesale paradigm shift in the underlying mathematics of trajectory generation. By integrating modern continuous thrust propulsion models with highly complex dynamical systems theory, they've unlocked, get this, over 2 million new, incredibly low-energy, highly viable routes to these asteroids.
Yeah, the magnitude of finding 2 million viable trajectories, it really cannot be overstated.
It's staggering.
Because for decades, orbital mechanics has been heavily constrained by a very rigid set of mathematical assumptions. And, those assumptions were brilliant for the Apollo era.
Right, they got us to the moon.
Exactly, and they successfully navigated the Voyager probes entirely out of the solar system, but they were inextricably tied to the hardware and the computational limitations of the mid-20th century.
So it changed.
Well, what Biolci's team recognized is that our modern hardware, specifically our propulsion technology, has vastly outpaced those legacy trajectory algorithms.
Yeah.
We have basically been trying to fly 21st century ion engines using math that was designed for chemical rockets.
That sounds like running a modern video game on a computer from the 1990s.
It's exactly like that. And by abandoning those legacy constraints and developing a less computationally prohibitive way to model multi-body gravity, they've drastically reduced the launch escape energy required to get these missions off the ground.
Okay, so to really understand why this new math is so groundbreaking, we first have to understand the flawed, kind of brute force way we've been exploring space for decades, right?
Yeah, the legacy constraints.
Right, so the contrast is where the genius of this new approach really shines.
Yeah.
Let's talk about the patched conics method. because for a long time, this was the absolute gold standard for NASA mission planners.
It was the only way to do it, really.
Right. And the mathematical foundation of this patched conics method relies heavily on something called the two-body problem. It simplifies that crazy magnetic thread chaos you mentioned earlier by stripping the universe down to just two interacting masses at any given time. Usually that's just the sun and the spacecraft.
Right. And it's an incredibly clever workaround for the lack of raw supercomputing power back in the day. In the two-body problem, you actually have an analytical solution.
Meaning you can solve it cleanly on paper.
Exactly. Thanks to Johannes Kepler and Isaac Newton, if you only have two bodies, you can perfectly predict their positions at any point in the future using relatively simple algebraic equations. The orbit will always be a perfect conic section, a circle, an ellipse, a parabola, or a hyperbola.
Hence the name patched conics.
Right. But the moment you introduce a third body, say, you have the Earth, the Sun, and a spacecraft all interacting, that neat analytical solution just vanishes. You enter the realm of chaos theory.
Like Henri Poincaré proved back in the late 19th century, right?
Yes. You can no longer solve it with a neat equation. You have to use numerical integration. You have to calculate the forces step by step, microsecond by microsecond, which is computationally exhausting.
Wait, so to avoid that computational nightmare for decades, the space exploration, the math basically pretended Jupiter, Mars, and even Earth didn't exist once we launched.
Essentially, yes.
That sounds crazy. That sounds like planning a cross-country road trip by drawing a perfectly straight line on a map and just assuming there are no mountains in the way.
It's a great analogy, but there's a good reason for it: computational pragmatism. Calculating multiple gravities at once requires a massive amount of computational power, so they effectively sliced the solar system up into isolated spheres of influence.
The Laplace spheres, right?
Exactly. When a probe launches, the math considers only the Earth and the spacecraft. The Sun is ignored. Jupiter is ignored. There, once the probe crosses an invisible mathematical boundary, the edge of Earth's sphere of influence, the software essentially drops Earth from the equation entirely and switches to a Sun spacecraft two-body problem.
So it treats the complex, overlapping gravity wells of the entire solar system as just a series of isolated sterile bubbles.
That is the absolute essence of it. You solve the geocentric hyperbola for the escape, you solve the heliocentric ellipse for the cruise phase, and you solve the target-centric hyperbola for the arrival. Then you mathematically, quite literally, patch these conic sections together at the boundaries.
That's wild. It's basically a mathematical fiction.
It is a brilliant mathematical fiction. But the friction between that fiction and the actual physical reality of the solar system, well, that has to be paid for, and it is paid for in fuel.
Because Earth doesn't actually stop pulling on the spacecraft just because it crossed some imaginary mathematical line.
Exactly. The actual trajectory drifts from the patched conic mathematical prediction. So to fix that drift, you have to perform mid-course correction burns. You spend delta V, meaning fuel, to force the reality to match your simplified math.
Man, and that reliance on delta V, that perfectly aligns with the hardware of that era, doesn't it? The chemical rocket.
Oh, perfectly. The patched conics method fundamentally assumes impulsive maneuvers.
Meaning explosive, right? It assumes that all velocity changes happen instantaneously, which, from a mathematical perspective, makes total sense if you are firing a massive chemical engine. You ignite hydrolox or hypergolic propellants, dump massive thermal energy at the nozzle, and generate thousands of kilonewtons of thrust in just a matter of minutes.
Right. The velocity vector changes so rapidly that, for the sake of the orbital integration math, you can treat the burn time as effectively zero.
It's an instant node on the path.
Exactly.
Yeah.
The math and the hardware were perfectly symbiotic, but there's a massive penalty. The Tsiolkovsky rocket equation dictates that if you want to perform these massive impulsive plane changes or orbital insertions, you need a tremendous amount of chemical propellant.
And propellant is heavy.
Very heavy. And that propellant adds mass to the spacecraft, which requires an even larger rocket to lift out of Earth's gravity well, which requires even more propellant. It's the tyrant of mass fraction.
Right, so we were optimizing missions purely to minimize flight time and limit the number of those impulsive burns, because every single burn required dragging tons of volatile chemicals into deep space.
Exactly. Chemical rockets are the hair in space travel. Fast, explosive, but they really limit your long-term options. The patched conics method was designed explicitly to string together these explosive, instantaneous nodes.
But the brute force math that worked for explosive rockets, it just doesn't compute for the new hardware we have now. The propulsion paradigm has completely shifted.
It has. We are increasingly moving away from chemical propulsion for deep space transit.
Right. We're moving in favor of solar electric propulsion, or SEP, things like gridded ion thrusters, Hall effect thrusters. And SEP operates on a completely different physical principle.
Totally different.
Instead of chemical combustion, we are using solar arrays to generate electricity, using that power to ionize an inert gas like xenon, and then accelerating those ions out the back through a high-voltage grid. And the specific impulse, the efficiency of the engine, is an order of magnitude higher than the best chemical rockets.
The efficiency is just staggering. A really good chemical engine might give you a specific impulse of, say, 450 seconds. A modern ion thruster can easily push 3,000 to 4,000 seconds.
Wow.
You are getting vastly more delta V per kilogram of propellant. But the trade-off is the raw thrust. The mass of those xenon ions is so incredibly low that the actual physical force imparted on the spacecraft at any given moment is minuscule.
How minuscule are we talking?
Well, if you activated a standard 5-kilowatt ion thruster right here on Earth, the thrust it produces wouldn't even be enough to counteract the friction of a rolling coin. It is roughly equivalent to the downward gravitational force of a single piece of tinder paper resting in the palm of your hand.
Wait. Okay, here's where it gets really interesting. Let's pause on that. Because the disconnect between the visual of, like, a towering Saturn V launch and the reality of deep space propulsion is vast. You're telling me I could push a multi-ton spaceship with the force of a sticky note and eventually outrace a chemical rocket?
Yes, because it's continuous. But if you only have that tiny fraction of a newton of thrust, you can't perform an impulsive maneuver.
Right, you can't just fire the engine for 3 minutes to enter an orbit like in the movies.
No, you have to run that ion thruster continuously for thousands of hours. You're accumulating that tiny acceleration week after week, month after month. It is the tortoise of space travel.
So how does the old math handle that?
It doesn't. NASA's old code literally couldn't understand or map routes for slow-burn technologies like SEP. In a chemical trajectory, you have long periods of ballistic bursting, where Kepler's laws apply perfectly, punctuated by brief burns. But with an SEP engine firing constantly, the spacecraft never actually settles into a clean Keplerian orbit.
Because the orbital energy is constantly changing.
Exactly. The semi-major axis is constantly expanding or contracting. The patched conics method completely collapses when you try to feed it a continuous thrust profile because it relies on the assumption of instantaneous state changes. You can no longer patch simple curves together. You have to integrate the trajectory over massive timescales.
And if your engine is only pushing with the force of a piece of paper, you are completely at the mercy of the surrounding gravitational environment, aren't you?
Absolutely. You can't ignore the Earth and the Moon anymore.
It makes me think, a chemical rocket is like a speedboat, right? You point it, hit the throttle, and you can largely ignore the ocean currents because you're just blasting over them. But a SEP-powered spacecraft is more like a sailboat.
That is a perfect way to look at it.
If you try to fight a strong gravitational tide with an engine that weak, you will simply be overpowered and dragged way off course. You have to learn how to read the currents and sail with them.
And the necessity of reading those currents is exactly what forced Bielchi's team to abandon the two-body patched conics approximation in the vicinity of Earth. If your thrust is that low, the gravitational perturbations of the Moon and the Sun are no longer rounding errors you can just correct later with a fuel burn.
They're dominant forces that dictate your trajectory.
Exactly. To accurately model how an SEP spacecraft navigates the Earth-Moon-Sun environment, you have to upgrade the mathematics. You have to use what's called the circularly restricted three-body problem, or CR3BP.
And the CR3BP introduces that gravitational tug-of-war. Instead of isolating the Earth and ignoring the Sun, the math explicitly models the spacecraft, moving through the combined gravitational topography of both massive bodies simultaneously.
Right. And the physical topology of space changes completely under the CR3BP. Well, in a two-body system, the gravity well is just a simple, symmetrical funnel leading straight down to the central mass. But when you have two massive bodies orbiting their barycenter, like the Earth and the Sun, their intersecting gravitational fields create a highly complex potential energy surface.
Like it's lumpy.
Very lumpy. The centrifugal force of the rotating reference frame combined with the gravitational pull of the two primary bodies creates specific regions where the forces perfectly cancel each other out. And these are the Lagrange points.
Right, L1 through L5, we frequently hear about those. Like the James Webb Space Telescope parking out at L2 or the solar observatories at L1. They are essentially points of equilibrium.
Exactly. If you navigate a spacecraft to a Lagrange point, it takes a virtually non-existent amount of station-keeping delta V to maintain that position. It's a gravitational balancing act.
So they serve as the perfect staging nodes.
They do, but the Lagrange points themselves are just the anchors for something much more profound in dynamical systems theory. The mathematics of the CR3BP reveals that these equilibrium points are actually connected by invariant manifolds.
Invariant manifolds, what exactly does that look like?
Well, to visualize this, you have to look at phase space, which maps not just the position of the spacecraft in 3 dimensions, but its velocity in 3 dimensions as well. So within that 6-dimensional phase space, stable and unstable manifolds emerge from the Lagrange points. They form these topological tubes that snake their way through the solar system.
Okay, so these are the invisible highways.
Yes. What's fascinating here is that space is not empty. It is a topological landscape of peaks and valleys of gravity.
So instead of using a speedboat to blast across the water, we are suddenly reading the ocean currents. We're parking our raft in a calm eddy of the Lagrange point and then catching a riptide, the invariant manifold, to drift exactly where we need to go for basically free.
Exactly. You expend a tiny bit of fuel to get into the manifold tube, and the natural gravitational gradient does all the heavy lifting, carrying you millions of kilometers into deep space. By mapping the CR3BP, we aren't fighting nature with rocket fuel anymore. We're literally surfing the solar system's natural gravity waves.
That is just so elegant.
It is. By coupling the continuous, highly efficient thrust of an INSEP engine with the zero-cost transit of an invariant manifold, Biolchi's team solved the massive fuel constraints that plagued all those early asteroid missions. You just use a little ion engine to gently steer between manifolds rather than fighting gravity to create your own path.
Okay, but navigating the complex currents near Earth is brilliant. But earlier you mentioned that integrating the CR3BP introduces a computational nightmare. If the three-body math is highly chaotic and incredibly sensitive to initial conditions, the classic butterfly effect where a microscopic rounding error on day 1 compounds into a million-kilometer miss by year 3, how do they actually run a simulation for a multi-year asteroid rendezvous without the computers just melting down?
It's a very real problem. The chaotic nature of the CR3BP means that long-duration numerical integration is intrinsically unstable. There are these things called Lyapunov exponents, which basically measure how quickly 2 slightly different trajectories diverge in a chaotic system, and they guarantee that computing a continuous, unbroken path from Earth to a deep space NEO and back is mathematically intractable.
The optimization algorithms will simply fail to converge on a solution.
Every time. So to solve this, the researchers had to decouple the trajectory. They employ a modular architecture.
A Frankenstein trajectory.
Yeah, Frankenstein trajectory. They break the mission into segments. They use the complex CR3BP math while the spacecraft is navigating the Earth-Sun Lagrange system, utilizing those invariant manifolds to escape the Earth's gravity well efficiently.
Right.
But once the spacecraft travels far enough into deep space, where the Earth's gravitational influence drops below a significant perturbation threshold, the software intentionally drops the three-body dynamics.
Oh, it reverts to the traditional 2-body heliocentric model.
Exactly, because at a certain distance, the complex dynamical topography smooths out. The sun becomes the overwhelmingly dominant force, and trying to model the Earth's distant microscopic pull is just a waste of computational resources that only introduces integration errors.
That makes total sense.
But the real breakthrough in the decoupling is how they handle the return trip. They don't run a forward integration from launch to return as one long math problem. They calculate the outbound leg from Earth to the asteroid. Then, completely independently, they calculate the inbound leg from the asteroid back to Earth.
Wait. So we're effectively running 2 completely different software programs and just duct taping the results together when we reach the asteroid. Why does separating the trip home from the trip there matter so much?
Because of that computational chaos we talked about. If you calculate a round trip as one continuous equation, a tiny variable change on day 1 completely ruins the math for year 3. By cutting the trip in half and stitching it together at the destination, you save massive amounts of computational power.
But if you calculate the outbound trip and the inbound trip as 2 completely isolated mathematical events, how do you reconcile them at the asteroid? The spacecraft is physically one continuous object. You can't just arrive at an asteroid with one velocity and instantly swap to a different coordinate system and a different velocity for the trip home without, violating the laws of physics.
Right, there has to be a physical bridge. And that bridge is established through highly advanced boundary value optimization.
How does that work?
Well, when the outbound trajectory arrives at the near-Earth object, it has a specific state vector, a precise position, velocity, mass, and time epoch. Now, the independently calculated return trajectory requires a very specific starting state vector to successfully ride the manifolds back to Earth. The gap between those two state vectors, that is the optimization problem.
Oh, I see.
The algorithm uses nonlinear programming to iteratively adjust the launch parameters, the manifold insertion points, and the SEPI thrust profiles until the state vector at the end of the outbound leg perfectly matches the state vector required for the inbound leg.
So they were effectively working the problem from both ends toward the middle, just tweaking the variables on both sides until the math perfectly aligns at the asteroid, allowing for a seamless transition. Duct tape.
High-tech mathematical duct tape, yes. They enforce continuity constraints. They ensure that mass, time, position, and velocity match perfectly at the boundary. And by doing this, they completely bypass the chaotic instability of a single continuous integration.
Okay, so the researchers built this brilliant, computationally efficient, slow burn friendly, gravity surfing mathematical model. What happened when they actually turned it on?
The simulation results were they were staggering. This mathematical architecture is so computationally efficient that they were able to run simulations on 80 different near-Earth objects, testing the entire parameter space of departure dates and flight times.
80 actual asteroids with relatively flat, low eccentricity orbits. And what did the model spit out?
Over 2 million distinct, viable round-trip trajectories.
2 million.
Yes. And they didn't just generate these in a vacuum, they benchmarked them against NASA's near-Earth object human spaceflight accessible targets, study the NHATS database.
NHATS represents the pinnacle of legacy trajectory design, right?
Yeah.
Utilizing standard impulsive maneuvers and traditional mathematical models.
Exactly. And when they compared the new hybrid continuous thrust CR3BP trajectories against the NHATS database, the required delta V for the missions was somewhat comparable. But the critical metric that plummeted, the one that really matters, was the launch escape energy, which is widely known in orbital mechanics as C3.
Okay, break C3 down for us, because that sounds important.
C3 is arguably the single most restrictive metric in mission architecture. It represents the square of the hyperbolic excess velocity.
So what does this all mean for you, the listener? Let's translate this into plain English.
Well, when a launch vehicle lifts a payload off the pad, it has to overcome the immense gravitational potential energy of the Earth. To send a probe into deep space, you don't just need to reach orbital velocity, you need to exceed Earth's escape velocity. The energy required to leave the Earth's sphere of influence with a specific remaining velocity. That residual speed is your hyperbolic excess velocity, is quantified as C3. And C3 scales exponentially with the required velocity.
So if your trajectory algorithm dictates that you need a massive initial kick to brute force your way onto an interplanetary transfer orbit, your C3 requirement skyrockets.
Yes. And high C3 dictates a massive heavy lift rocket. If you need a C3 of, say, 30 square kilometers per second squared, you might need a Falcon Heavy or an SLS just to throw a modest probe into deep space.
And those cost hundreds of millions of dollars. But by utilizing the invariant manifolds of the Earth-Sun Lagrange points, the new trajectories effectively siphon energy from the dynamical system itself.
Precisely. The spacecraft isn't relying entirely on the launch vehicle to provide the kinetic energy required to reach deep space. It's riding the gravitational gradients. Consequently, the C3 requirement drops precipitously.
So lower launch escape energy means you need way less rocket power to get off Earth, which translates to a massively cheaper mission. A mission that previously required a dedicated heavy lift rocket could potentially hitch a ride on a medium lift vehicle, or even launch as a secondary payload. It opens the door for a gold rush of cheap probes.
If we connect this to the bigger picture, the fact that they found 2 million viable paths for just 80 asteroids proves that the solar system is infinitely more accessible than our old brute force math led us to believe. The economics of asteroid exploration fundamentally shift. It opens the inner solar system to university research teams, private resource prospecting companies.
Smaller national space agencies, anyone, really. But 2 million trajectories is an abstract number. Let's look at how this new math handles specific, real-world rocks floating out there right now. Because the true test of an algorithm isn't just lowering the C3 for easy, simple targets. It's handling the chaotic outliers.
Oh, absolutely. And the researchers highlighted two specific case studies that really push the boundaries of orbital mechanics. The first one is asteroid 1991 VG.
What makes 1991 VG so special?
It's a fascinating dynamical object. Its orbit is so similar to Earth's that it routinely enters our immediate neighborhood, and occasionally it even gets temporarily captured by Earth's gravity as a quasi-satellite or a mini-moon.
Oh, cool.
Right. But because it's synodic period, the time it takes to return to the same position relative to Earth is so complex, plotting a rendezvous requires incredible precision. The legacy approach would typically struggle with all the overlapping perturbations.
But the hybrid algorithm plotted an alternate gate transfer.
It did.
It mapped a path where the spacecraft launches from Earth, navigates to the L1 Lagrange point directly between the Earth and the Sun, and just parks. It waits for the precise epoch when 1991 VG drifts through the localized phase space, initiates the rendezvous, and then, rather than fighting its way back to L1, it departs via a completely different manifold.
Exactly. It utilizes a heteroclinic connection. It transfers from the stable manifold associated with the L1 region directly into the orbital regime of the asteroid, and then for the return, it couples onto a manifold that winds toward the L2 Lagrange point, which is located on the far side of the Earth, opposite the Sun.
I love this. It's like sneaking out the front door, visiting a mini-moon, and then sneaking back in through the back door. It turns orbital mechanics into a beautifully choreographed dance.
It really does. The spacecraft effectively uses the gravitational currents to sweep across the Earth's orbital path, intercept the target, and ride the wake back to the other side of the planet. And the delta V required for the actual transit is negligible because the manifolds are doing all the work.
It transforms trajectory design from a brute force artillery problem into something closer to fluid dynamics. But 1991 VG, while dynamically tricky, still exists relatively close to the ecliptic plane. The ultimate stress test for any trajectory algorithm is a highly inclined, highly eccentric orbit.
Which is why their second case study focused on Apophis.
Apophis, the famous one?
Yeah, Apophis is notorious in the astrodynamics community. Its eccentricity means its velocity fluctuates wildly as it moves from periapsis to apoapsis, making phasing a rendezvous incredibly difficult. But the true penalty comes from its orbital inclination.
Right. Apophis does not orbit on the same flat, two-dimensional plane as the Earth. Its orbit is tilted.
Highly tilted. And inclination changes are the most punishing maneuvers in all of spaceflight.
If a spacecraft is cruising along the ecliptic plane, and it needs to pitch up to intercept a target like Apophis, it isn't just a matter of steering, is it?
No. Vector mathematics dictates that you effectively have to cancel out a massive portion of your existing velocity vector in the horizontal plane and re-accelerate in the vertical plane. It is catastrophically expensive in terms of delta V.
And performing a deep space inclination change using only a low-thrust SEP engine, that's often mission-ending, right?
Usually, yes. The engine simply cannot impart enough force quickly enough to crank the orbital plane before the spacecraft overshoots the intercept window. In a legacy two-body framework, Apophis requires massive chemical burns.
So how did the algorithm handle it?
Beautifully. Biolchi's algorithm leverages the CR3BT dynamics to bypass the plane change entirely.
Wow.
By utilizing the complex three-dimensional topography of the invariant manifolds near Earth, the spacecraft can essentially use the Earth's gravity to crank its inclination naturally as it escapes the local system. The manifold itself is heavily inclined, providing the necessary out-of-plane velocity without expending onboard propellant.
That is incredible.
Yeah.
The algorithm doesn't fight the geometry of the solar system. It uses the geometry to solve the physical constraints of the engine. It proves its robustness. It doesn't just work in easy, flat conditions. It works in the messy reality of space.
Exactly.
Which brings us to the final critical phase of the architecture. Because we've figured out how to launch cheaply, coast on gravity highways, and visit tricky asteroids. But the most dangerous part of any space mission is the very last step, coming home. Whether you are returning a sample of rare earth metals from an asteroid or bringing a crew home, the deep space transit is only prologue to the thermal nightmare of hitting the Earth's atmosphere.
Yeah, the atmospheric interface is the most unforgiving regime of any mission. When a spacecraft returns from deep space, it typically arrives with immense hyperbolic excess velocity. It slams into the upper thermosphere at 11 or 12 kilometers per second.
And all that kinetic energy of the spacecraft is instantly converted into thermal energy through shock layer compression. The temperature at the stagnation point on the heat shield scales with the cube of the velocity.
The cube of the velocity, meaning a small increase in arrival speed results in a massive exponential increase in the heat generated.
Right, so a capsule hitting the atmosphere at 12 kilometers per second requires a significantly thicker, heavier, and more complex ablative thermal protection system than a capsule arriving at, say, 8 kilometers per second.
And mass is exactly what we are always trying to eliminate. Every kilogram of phenolic-infused carbon ablator on the heat shield is a kilogram of scientific payload or asteroid regolith that you cannot bring back.
And traditional legacy trajectories, optimized purely for transit time, often resulted in those brutal, high-energy direct entries, didn't they?
They did. But the manifold return trajectories generated by this new algorithm fundamentally alter the arrival dynamics, because the spacecraft isn't dropping straight down the gravity well.
It is riding the stable manifold back toward the Earth-Moon system. The topological tube of the manifold forces the spacecraft to take a winding, circuitous route, bleeding off kinetic energy and gradually matching its velocity vector with the Earth before it ever touches the atmosphere.
Exactly. The relative velocity at atmospheric entry drops significantly. The spacecraft eases into the gravity well rather than plunging into it, and this translates directly to reduced peak heating rates and lower total heat loads.
So hitting Earth's atmosphere at a slower speed means the spacecraft requires significantly less heat shielding. It's ironic. We spent decades obsessed with going fast, but the real secret to unlocking the solar system was learning how to go slow.
That's entirely it. It's a massive win-win. The thermal protection system can be drastically lighter, further improving the mass fraction of the entire architecture. Furthermore, the lower structural loads broaden the entry corridor, increasing the margin of safety for the vehicle.
The compounding efficiencies are just extraordinary to think about. You reduce the C3 at launch, meaning you use a smaller, cheaper rocket. You use solar electric propulsion, replacing tons of chemical propellant with a few tanks of xenon gas. You navigate the chaotic Earth-Sun regime using zero-cost invariant manifolds.
You seamlessly stitch the coordinate systems together in deep space to bypass supercomputer constraints.
Yes. You utilize the three-dimensional geometry of the manifolds to intercept highly inclined, eccentric targets like Apophis without suicidal plane change burns. And finally, you bleed off the velocity naturally on the return, shedding hundreds of kilograms of heavy thermal shielding.
It is a complete architectural overhaul of how humanity interfaces with the inner solar system. It forces a complete reevaluation of what we consider physically possible. For the better part of a century, the aerospace community has assumed that the primary barriers to deep space industrialization and exploration were materials, science, and propulsion. We assumed we needed to forge lighter alloys, engineer denser chemical propellants, or develop nuclear thermal rockets to make the asteroid belt economically viable.
We viewed the solar system as an antagonist to be overcome with raw, explosive power. Stepping away from the brute force of chemical rockets and simplistic two-body math, and embracing the elegant, computationally clever, gravity-surfing reality of three-body math and solar electric propulsion, it changes everything.
It really does, because the physics of the solar system weren't the actual barrier. The barrier was the mathematical lens through which we were viewing the problem. The legacy equations, built for an era of slide rules and early mainframes, created artificial walls in orbital phase space. The energy wasn't lacking. It was simply hidden within the chaotic dynamics of the three-body problem, waiting for algorithms sophisticated enough to map it. Biologist's work proves that the most profound advancements often don't come from applying more brute force, but from increasing the computational elegance of the models we use to interpret nature. It leaves us with a lingering concept to mull over. We often think the greatest barrier to space exploration is physical building bigger rockets or stronger materials. But as this research shows, the most profound barrier wasn't physical at all. It was our imagination and our mathematics. What other impossible boundaries in your life or in our world are actually just waiting for a slightly better algorithm?
A brilliant conceptual framing. The universe often yields not to the loudest explosion, but to the most precise calculation. The invisible highways of the solar system are mapped and waiting. Keep questioning the models, keep looking up at the bustling cosmic neighborhood right in our backyard, and we will talk to you next time.